All right. So, good day, class. So, this is a recording for those who haven't catch up on our course introduction and our lecture one. I'm going to skip the course introduction. You can read that in our uploaded canvas. You can see the rules there and make sure to read that, especially before taking the exams. I'm not going to repeat myself on that. And I don't want to hear na hindi ko discuss siya or anything. It's posted there. You can read it. Okay? So it's rules regarding what to do during exams. You know my rules, face to face, yeah. No other accessories during exams, no calculators, cover, no smartwatches, no ID, no ID laces, no phones. Everything is in the bag, and bag should be placed under the bed, under your bed tuloy, under your chair, and walang hiraman ng liquid eraser or anything like that. Okay, or even eraser, pencil eraser. No. Scratch paper, that's debatable, depending, but I usually just give out your test exam with your with the back part as the as the test paper. What else? Rules and rounding off. Yeah. So maintain 3 to 4 decimal places when solving a problem, and then on final answer you round it off to 2 decimal places when applicable. Okay. Tapos please read the problem read the problem. I've seen what your mistakes are. It seems you memorize more the solution than understanding really what the solution is all about. Okay? Why memorization does help. Reading the problem also really helps, especially if you already know how to solve it in the first place. Okay, that's pretty much the course intro. So here for this summer edition, I'm just gonna talk about the stress. Gonna go over some concepts lang again, and hopefully this is just a total recap lang on you guys. This is pretty much the what to expect during the summer term. So we have the stress, what are the concepts behind this, the normal, shear, actual, torsional, and bending. These are pretty much basics pa nga. Then of course, I'm gonna jump back and forth sometimes after normal and shear and actual. We're gonna be talking about pressure vessels and spears. So in thin walled pressure vessel, thin walled spear. Then, of course, when we're talking about shear and moment diagram, we're going to go back again to bending, more on bending stresses. And then, of course, more sample problems. And pretty much it. Yep. So, as I've discussed last Friday, I'm sure uh, reviewing your concepts back in statics lectures 4, 5, and 6 will definitely help getting the moment, establishing your free body diagram, whether 2D and 3D. So these are the sample problems we took in here. We're not gonna go for Cartesian vector notation anymore that much. So here we have some more 3D problems. We're gonna go more on beams, the reactions, and couple moments. And then of course, establishing yung mga reactions na yan, um, understanding that there's an algorithm here, that there's a step-by-step process. You draw your FPD, you establish your equation, equilibrium, then solve. Then of course, making sure like you know how to orient yourself, whether 2D or 3D. So here's a classic example. And of course, it's kind of stresses. We can solve these members by sections, So and also we have to assume, is it really in tension or compression, because we have in actual loads, we have a compressive and tensile stress, and of course tension, and of course we have the pull and the push action as well there. And of course, if we assume this particular direction and the answer turned out to be negative, it means our assumed direction is wrong. Okay, so here we are. So just like in trusses, we can't solve this by section rin. So we have to choose a segment where it matters, and sometimes we need the entire segments to solve for unknown forces before we actually solve the segment that matters. You will get that along the way. Then of course, summation of forces equals to 0 as well as for moment. And of course, just a brief recap, rin, we have yung mga reactions na to. And for for mechanics of deformable bodies, we care now about the internal forces happening in it, in direct relation to the external force being applied to the body. And of course, meron tayo, per connection, there is a equivalent reaction here. You can read that through. These are just lessons from back then, uh, in, in, in our statics days. But primarily, we'll be dealing with a lot more rocker, smooth conducting surface, cables, roller and pin, smooth pin and hinge, especially that, for our shear stress. So we need to determine that. And of course, fixed supports. There's also some 3D here. So especially this one, you can read. So there's the roller, ball and socket, single journal bearing, single journal bearing with square shaft. Okay, single thrust bearing. Okay, the important thing here lang naman is that per connection, there's a particular movement that they're trying to restrict. And normally that movement that they're trying to restrict is the reaction force. Let's go for an example here. Here is a single Smith, wait now, let me just zoom that in. Here is a smooth uh, single smooth pin. And as you can see here, it freely moves. So this is 3D, you know. So this is our x-axis. This is our y-axis, and this is the z-axis. So it freely moves along the x-axis, but it restricts vertical, so z, and y movement, y-axis, and it also restricts ffx in terms of that. But in terms of moment, it allows moment about x, but it doesn't allow moment about y. It doesn't allow moment about z as well. So that's pretty much it. Whereas to comparing it to the fixed support, now it's really fixed, so it's preventing all three movements along the x, y, and z forces, as well as it's also preventing torque or moment about the x, y, and z axis. See? So if you can't memorize them all, just think of the logic. Okay, this is the type of connection. You could also ask, what sort of forces is it trying to restrict? That should be my. If you know the answer now to that, then then the reaction forces should be those forces, the forces that you're trying to that this particular joinery or connection is trying to restrict. Okay, so now with the engineering mechanics, it's just a brief overview. You've seen this definitions before, starting on static days. We started with statics and dynamics of rigid bodies, and primarily we're dealing with internal. We're dealing with these two type of mechanics, statics and dynamics, primarily focused on external effects on rigid bodies. And with fluid mechanics here, just gonna skip this over lang for a bit. Um, Essentially, it's statics and dynamics, but for fluid mechanics. It's also a combination of deformable bodies, but we're talking about fluids here, so that means gas and liquid. Okay, but hopefully you pass enough and you get to know more about that on third year. It's a pretty straight shot formula. There's a lot of derivation there, but hopefully you get to understand. But with mechanics of deformable bodies, now we're not only taking into account the external forces, but we are interested now on what effect it does on the internal body of our membrane here for deformable bodies. So there we go. We also take into account the deformation and are now a matter of interest. So the weight of the object is of interest now, and the weight of the material itself, not just the load, because there's such a thing called failure due to its own weight, so to speak. Okay. So to understand what are the kinds of loads we're dealing with here, the internal forces. Technically, that's the continuation sana ng statics natin, but I thought na it's gonna be discussed again here in mechanics in the deformable. So this is my chance again to continue the story. So we're talking about internal forces dito, or what we call internal loads, right? Okay. So imagine you have a potato, okay, and uh, and this is the potato, and the potato is with four external forces applied as shown. Okay, so let's do that here. There we go. Okay, I just traced the diagram, and I don't think Hibler has a better drawing, but I like the representation here. It's a lot simpler. It's straightforward. So I'm gonna use what your two professors already done. Okay, And we're here to identify the internal loadings. Okay, so we're gonna chop that up and see what's the inner works of the forces inside this particular potato. No? So I'm gonna show them all. So we have axial, we have torsional, we have shear, and we have bending moment. Okay, so for axial here, from the word axial, it's primarily it's about pulling and or pushing. Okay, and you notice here there's two forces again. So pulling we have tensile, and pushing we have compression, and it's generally applied and perpendicular to the cross section of this particular potato, and normally it's done along the axis. Okay, so in this particular case, binaliktad niya lang yung x, y, z, you know. So it's really weird. So baliktarin mo naman, gano'n rin naman eh. And with shear forces naman, this is done in parallel naman, ano. So meron tayong mga tinatawag na longitudinal and tangential forces, but I guess that's more on the torsional pala, no? So these are components of the total resistance to sliding portion. So meaning this cross section, tong area na to, the force is being applied in parallel sa kanya, no? So ganyan. So whether at y-axis or z-axis here. Okay? And then for torque or torsional moment naman, this is moment, oh. This is the resistance to for twisting members. Okay? And then finally, there's bending moment. Okay? It measures the resistance to bending about the x or z axis, at least relative to this figure here. Okay? This is when we're talking about 3D. So when we're talking about in objects in 3D, we normally deal with the actual or normal force. Could be compression, could be tensile. We have shear forces, we have torsional moment or torque. Then of course we have bending moment for 3D. But if our potato is only subjected to complanar system of forces, or simply 2D, we can consider only be dealing with normal force, shear force, and bending moment. Okay, so just like so. This one is directly from your book, Hibbler 2011, page 9. Okay. Earlier, I've shown some type of connections and their particular reactions. So again, these are the common type of connections that we'll be primarily be using, whether it's going to be 2D or 3D. So we have a cable, we have a roller, we have the smooth support, we have external pin, internal pin, and finally fixed support. And just like I said, to determine the reaction force, you just have to know what kind of force is this type of connection trying to prevent. So for example, here it's trying to fall down, so the reaction must be here. This one, so it's trying to prevent going down further, this roller, so we have to put it up. That's the reaction. Smooth surface, so we know with smooth surface it has to be a particular perpendicular reaction force. And external pin, it's preventing a vertical and horizontal movement, so that's got to be x and y. Internal pin is also preventing X and Y movement. With fixed support, it's not only preventing horizontal movement and vertical movement, it's also preventing any particular bending or moment here. That is for coplanar systems. Okay, and of course, once you determine now your reaction forces, or basically once you completed your free body diagram, now it's time for you to establish your equations or equations of equilibrium here. Here, equations of bodies require both a balance of forces. Okay, we're still talking about rigid bodies. It has to be stationary. It has to be rigid. And it just so happened we're interested in knowing what's happening inside by a certain degree, by how much force is this taking in inside back. So we know there's an external load. We know it's going to be rigid, but by how much? But by how much? Okay, but when it comes to failure na, okay, that's a totally different topic. We'll be talking about that strain. Okay, so here the summation of forces per and moment should be equal to 0, whether we're dealing with 2D or planar systems or 3D, so x, y, z here. There we go. So I'll just put here some general procedures lang naman. If you feel free to read it lang on your own time. It comes it came straight from your book, so you can read it there. And but you'll be able to understand these processes further if you're just gonna solve some sample problems. Okay, so here's one. The animations here is gonna be wacky. Okay, so just bear with me here. So we're here to determine the internal loading action on the cross section at C on the cantilevered beam shown below. So what we have here, we have a cantilevered beam. We have a un not uniform distributed load, so in the shape of a triangle. So we're only interested where? We're only interested in the cross section C, we can solve it either segment AC or segment CB. So we need to, pick a side. In this particular case, I chose CB so that I don't have to involve this guy. Okay, I don't have to moment pa or anything like that. So ito lang. Okay. And then from there, but I need to know what is the weight per meter distribution at point C. So there we go. All right. So in this particular case, it's a lot simpler since we can use ratios of um, uh, similar similar triangle ratios to determine the weight per weight per length uh, force here. Okay, weight the W basically. So once I did that, 270 over 9 equals to W over particularly 6. Similar triangle. Okay, and then our W will be 180 Newton per meter. And from that end, we can rewrite now our FBD. And the next step here, if you recall our if you recall our statics lesson, lecture 5 and 6, is after we determine we need to determine now our concentrated force. So we need to convert this particular uneven distributed force into one concentrated force. And we need to determine where it's going to be applied. Since this is a triangle, we can determine that by geometry, the concentrated load is somewhere 2/3 or 1/3 from this particular point. And 1/3 from here, that will be 2 meters, and the rest here is 4 meters. Hence, we got these dimensions here. So, so if you have questions, please, it's just a matter of geometry and proportion. Now, with the concentrated load, we just have to determine the load under this particular curve lang naman, or in this case, under this line. So it's just the area of triangle, basically. So what's the area of triangle is basically base times height divided by 2. So we got base 6 times height, 180, divided by 2, that will be 540 newtons. So that's the concentrated load at 2 meters from point C. Then after that, we need to showcase the reaction forces here. So this is a cantilevered beam. It has it's preventing the Y movement or shear, and also preventing horizontal movement. In this case, that will be the normal force, and also it's also preventing bending moment here. So, and we're dealing with a problem that's planar, so we don't have any torsional moment here or torque for that matter. Okay, okay. So this is our assumed directions here. So after this, we now establish our equations of equilibrium dito. There we go. So we start with the f of x with NC. NC is now negative. As you can see here, I established that going to the right is positive. So meaning minus NC here equals to 0. Divide the -1. That will mean our normal force here is 0, pretty much. Then for vertical, going up is positive. That will be our shear minus our 540 newtons. This is not included. This is a rate. Okay, that's a weight per meter. Okay, so that means our shear is experiencing 540 newtons in force. And then finally, the moment about C. So there we go. So there's already existing moment, MC. We're trying to determine that bending moment there. Since this is counterclockwise is positive, this is going clockwise, that will be negative MC. This is going clockwise as well, so negative 540 times 2. And that's pretty much it. So that should give us around 1080 Newton meter clockwise because it's going to the negative. Easy, right? Okay. Now, for sample number 2, here, I think this is a very familiar problem with you guys. So we start here by reading the problem. The 500 kilogram engine is suspended from the crane boom shown below. Determine the resultant internal loading acting on the cross section at the bottom E, at the point E. So here, we're interested at E. So technically, if we're gonna solve this properly, interesado lang tayo sa segment AE. However, we don't know much of the forces here. Even if we started here, we know that this is a pin reaction, so it's preventing what? It's preventing X and Y movement as well. Okay? And but we don't know what AX is, we don't know what AI is. But what we do know is we have a 500 kilogram engine here, which we will convert to weight later by multiplying to acceleration due to gravity. Okay, so in this particular case, we know that we're going to AE, but we still have to solve unknown forces here. So here we have a cable here that's FCD, but we don't know the forces. So we have to solve it unknown members first. Okay, so this is a two-member, just like in trusses lang naman. Okay, so we build the FBD first, and our FBD would look something like this. And I got this by 1.5 divided by 2 meters, 1 plus 2. I got the ratio of 3 over 4. So I just put that here and then got 5 by trigonometry, by Pythagorean theorem. And we have yung AX here and AY. And that's pretty much it. So here we have 1, 2, 3, 4 unknowns. What we do here is we clamp this up lang muna by getting the moment about point A so that we have only two unknowns dito. One unknown na lang. So from there, by getting the moment at point A, we will get FCD at 12,258.25 newtons. Yeah. And after that, we can now get the other forces such as in AX and AY by getting the summation of forces in X and Y, with AX at 9,806, 9,106.6 newtons, and then finally AY at 2,451.65 newtons. Okay. So it seems to me that my assumption of the directions ng FBD is correct. Okay. All right. Next up here is yeah, I told you the order of the animations are messed up, you know. So we're not yet done here because we need to determine the internal loadings here. So now that we know all forces here, we can now focus on segment AE here. So focusing on segment AE, we have this particular here. So we have the pin here. We have AX and AY, so it's preventing, you know, X and Y movement here. But in this particular section, there's a tendency to bend. There's also the shear moment and also the normal force here. Okay, so assume that the moment is gonna be what, counterclockwise here. Let's hope I'm wrong, or let's hope I'm right there. So with that, all we have to do na lang is set up again our equations of equilibrium. So summation of forces across horizontal, AX plus NE, that will give us negative 9806.6 newtons. So instead of going to the right, it should be going to the left. So there's a bit of compression going in there. Next up is Y forces. So that will be VE minus AY. So that would give us 2451.65 newtons. So we got that direction right. And finally, moment about E, I guess. Yeah, so moment about E. So we have ME. That's counterclockwise. So that's positive. Minus plus AY and whatever in distance that from E, so that's 1 meter. So that's gonna be negative 2451.65 Newton meter. So here it's negative because I assume the direction of our bending moment here should be counterclockwise. So it should be clockwise. Okay, so there we go. All right. So that's for sample problem 1 and 2. We can continue again with sample problem 3. And I'll pause the video here.